Hey, math fans. Welcome to one of our final editions of Math That Matters. Today we'll be talking about AM6, Awesome Math 6, and it's going to be Sum It Up Part 2. It's going to be our fourth lecture on the basic ideas of calculus and taking the infinite and somehow finding a container that's finite that can hold it so that we can quantify the infinities and make use of these amazing and marvelous principles that for some reason humans can comprehend. And I think about that verse that says that God has set eternity in the heart of mankind. And I think there's just something about forever, something about infinity that we're attracted to, we're drawn to. We want to live forever. And for some reason, even the principle of eternal life and the idea of the infinite draws us to I guess the idea of an infinity that makes us want to understand it in every way possible. And maybe it's that God has given us the calculus and these other sorts of maybe analogies or illustrators of the more important things of life. So let's get right into it. I'm going to share my screen with you. Run into this PowerPoint that I put together. So an application that's similar to the last lecture, Awesome Math 5, so this is just Sum It Up 2. So it's the same idea. So if you didn't get that down real well, you could go back to the other video, check out some of those things with particularly this idea of an integral. An integral is a special kind of sum where basically we're taking like the height of a rectangle times the width of a rectangle. And we're just doing a whole bunch of those. In fact, we're doing infinity rectangles areas. But the principle applies even if we don't have rectangles anymore. So if we just have a multiplication problem of something times something else, but we want to do it over and over and over again, maybe where this something right here isn't always the same, then we can do this calculus thing called a definite integral. And I showed you at the end of the last video a fast way to do this, to find area under a curve exactly using what was called the power rule. So we're going to make use of that today as well. Here's my biblical basis for today's topic. Got a couple of Bible verses for you, but Jesus replied, "My Father is always working and so am I." So today I thought we would talk about work, the idea of work, well, not just as a reflection of us image bearers of the Creator who is always working, and therefore our work is a gift given to us, but literally work, the work of physics, because work is simply a multiplication problem. So in a non-calculus based physics class, we would look at, I have a book right here. We'll just say this book is maybe, I don't know, 3 pounds or something like that. And maybe I want to know, how much work would it take to take this 3-pound book and lift it a distance of, say, 2 feet? And that's actually pretty easy to calculate. Work, by definition, is force times distance. And using the imperial system of measurement, we're just talking about pounds, 3 pounds, times a distance of 2 feet. 3 times 2 is 6. And the unit there would be foot-pounds, which is kind of an interesting thought. So if I do 6 foot-pounds of work, that's like lifting 1 pound 6 feet, or lifting 6 pounds 1 foot, or in fact, the illustration was lifting 3 pounds 2 feet. Now, if we were in the metric system, we'd have to do a little bit different calculation because force would be measured in newtons, and we would need to take the mass or the weight of the book in kilograms times the acceleration of gravity, 9.8 meters per second squared. And then when we get that force, we'd have to multiply it by distance, and that would turn into a work in a measurement called joules. But for this lecture, I'll leave that alone because it's a little bit easier and more accessible to kind of understand force as pounds, like how heavy something is, and work as pounds times a distance that we're moving those pounds. But, and this is where it gets more interesting and where calculus becomes necessary, what if the force is not a constant? So I had that book and I was lifting it, but it stayed the same weight all the way through the action. But what if it was a spring, and I was pulling a spring. If you've ever pulled a spring or even pushed a spring, what you realize is you can maybe pull it for a while, but it gets harder and harder and harder to pull. So it actually takes less work to pull a spring just a little bit, right? As it's got its resting length, and then you pull it a little bit. I should have brought my spring, but it was it's locked in a room right now. So I pull a spring just a little bit, and it doesn't take that much force. But once I've stretched a spring out a long ways, it takes more force. So the force isn't a constant, even though I can take a particular force and move the spring a distance, and I could do force times distance and get an amount of work, but it would just be an approximation, because that force, the second that I move and stretch that spring, the force becomes something different. So that's why this problem is definitely more interesting. And actually, you'll see it's not that different from the water tank problem, where we had some water escaping. We knew how fast it was escaping a tank, and we wanted to know how much water left the tank after a certain amount of time. So we're going to be looking at springs today a little bit, and we're also going to be looking at hanging cables. So if you think about a cable that's maybe hanging over a ledge, or a chain here is hanging over the edge of a table, or a chain could be hanging over the edge of a building. And so we're going to give you an illustration or example problem here. Suppose we had a 100-foot chain that weighs 5 pounds per foot, hanging all the way over the edge of a building. So if you kind of picture this as a building, the chain is actually 100 feet long, and the whole thing is hanging over the edge. And we want to actually just pull the chain to the top and calculate the work required to do that. But what you might think is, well, initially, if the chain is all the way hanging over the edge, maybe I'll just, I'll stop my share and let you look at my whiteboard here for just a minute. So we've got a building. Doesn't really matter how tall the building is. We got some chain that's hanging over the edge of this building. And the chain is 100 feet long. And remember, the chain is what I say. I think I said it was 5 pounds per foot. That's the density. So 5 pounds per foot times 100 means we have 500 pounds of chain hanging over the edge right there. So the thing is, once we start pulling this chain to the top and maybe coiling the chain at our feet, there's actually less and less chain hanging. So it's going to be really hard at first, maybe. You got to be really tough to pull 500 pounds of chain up. I mean, I could probably do it. Who am I kidding? Of course I couldn't do it. It'd pull me over. I only weigh 160 pounds. So, but if you had a winch or something like that, it's going to be a lot more work to pull it when the chain is long. And as the chain gets shorter and shorter, we're actually pulling less weight. And so there's less work to do in pulling that chain to the top. But if we could just kind of say, well, what if we pulled it up like, 10 feet, and then there's 90 feet of chain left. So that weighs less than 100 feet. And I just kind of pretended like it was 100 times 500 pounds of, I feel like 5 wasn't the number I used in my example. We'll look back at the PowerPoint in just a minute. But once we pull the chain up like 10 feet, again, it weighs less. So we can take that distance that we pulled it and how heavy it was when we pulled it that distance and kind of approximate the bit of work that we expended to get that chain up, say 10 feet or whatever it might be. So we can split this up into increments and approximate the total work. Well, let me run back to my PowerPoint and make sure that I've got the right numbers here. Uh, 5 pounds, 100 feet times 5 pounds would be 500 feet. Yeah, so there, I actually did pick the right number. So here's the formula for work. Work is force times distance. And so it's kind of seems like the answer could be, although you can see it's not, I have 500 pounds of chain hanging 100 feet over the edge of a building. And if I pull that up, force times distance, 500 times 100, 5 times 1 is 5 with 4 zeros, 1, 2, 3, 4, that's actually 50,000. And that unit would be foot-pounds of work. So you might think, Well, that seems kind of reasonable. It's just force times distance. But you have to remember that the force is how heavy the chain is. And when you pull that chain and pull it and pull it and pull it, it actually gets lighter and lighter and lighter because you pulled some up and maybe coiled it at your feet. So with every next pull, you're actually lifting less to pull it up and less to pull it up. So if you actually did the 500 times 100 and got 50,000 foot-pounds, that's way more work than you actually do, but it's an approximation. So kind of like the water tank problem, what I did was I said, well, when there were 100 feet of chain hanging down, there was 500 pounds. But then if I lift a distance of 10, I pull it so that there's 90 feet hanging over the edge. 90 times 5 is 450. So you can see it's kind of like the work that I just did. If you take force times distance and you approximate it high, you could say, well, it was kind of like 500 pounds times a distance of 10 feet would give me an amount of work, an approximation, an over approximation. Because again, as soon as I pull it up, the chain gets shorter, and so I'm doing a little bit less work. Or I could have said on the low end, the first 10 feet of pull was about 450 pounds. Or like the water tank problem, we could have just split the difference and said, well, the average is kind of like 475 pounds. Sometimes it was more and sometimes it was less. So, but essentially all we really have to do is calculate a little bit of an average amount of work done here and then do it again. If we're going from 90 to 80 and we're just taking a force times a distance, we could say, well, I think in this distance of 10 feet, if I approximated the force to be, say, 450 over those 10 feet, 450 times 10 would be 4,500 foot-pounds of work just on that 10-foot pull from 90 to 80. And you could do it again and again and again. So if you look at this, if I just say a force of 500 pounds times the first distance of 10 feet, plus then a force of 450 pounds times a distance of the next 10 feet, plus 400 pounds times a distance of the next 10 feet. You can see the pattern here. I'm kind of overestimating how much work I'm doing because each 10-foot increment gets a pull of the bigger number. Or I could have started with 450 here, and then I would have gotten a little bit less work total than I actually did. But you can see what we have here is the sum of a whole bunch of multiplication problems. So really it's called a Riemann sum, the sum of f of x times dx, a force times a distance, plus a force times a distance, plus a force times a distance. And we can approximate this, if you add all of that up, to 27,500 foot-pounds, which is definitely a lot less than the other approximation that we knew was way too big, 50,000 foot-pounds. But of course, we could make our approximation better simply by picking some numbers that might be more representative. Like that force certainly of the first 10 feet of pull wasn't 500, nor was it 450. It was bigger than this, it was smaller than this, split the difference. So there's a way that you could make some better approximations. But essentially, if you looked at this on a graph, we're really just finding areas of rectangles, like a height times a width plus a height times a width over and over and over. But ultimately, what we like to do is we'd like to make our approximation best, not just better. Best means exact. It means no mistakes, no errors. And in order to do that, what we need is we need a function for the force at every instant. And I guess when I say instant, a force at every different x value from 100 all the way down to 0. So it probably makes sense to you to think about the force function just being 5 times x if x is the length of chain that is hanging. So of course 5 times 100 is 500 and 5 times 90 is 450. So this force function of 5x is something that we can use to find every single different force for every single different x value traveling from 100 all the way down to 0 feet, which means 0 feet means we've pulled it all the way up. And the cool thing is, remember, we've got this powerful, powerful thing called a definite integral, whereby we can take some function that's changing and basically do this multiplication problem, some changing y value times some delta x, and add that and add that and add that and add that infinity times if we want to. We could make infinity rectangles and have no error. And that is exactly how we calculate work. Work is force times distance, but if the force keeps changing and I have a function that tells me how much force is required, if I just do the integral from some starting to some ending x value of the force function times delta x, that is a way to calculate the work. It's the sum of the little bits of work done, but the force gets to change and I get to be completely accurate in this. So that's pretty exciting. So let's actually do that. If the force function is 5x, so basically 5 times x is the length of cable hanging over, and that length of cable is going to be, we're going to sum up, these are bits of work from 0 to 100. Remember the power rule on 5x. If I want to take what's called the antiderivative of 5x, I would just write 5x to the 1 more, because the power is 1 here, so 5x to the second over 2. So because the power is 1 here, I just add 1 to 1 and I get 2, and I make that the divisor as well. And what we like to do, this is from the fundamental theorem of calculus. In order to find the area under this curve, I find the antiderivative of the function. And it says, it is said that I evaluate, that's not spelled right, is it? Evaluated, that sounds like a an ululation or something like that. Evaluated from 0 to 100, that just means I plug in the 100 for x, I plug in the 0 for x, and I subtract. And what you see here is that what we get when we plug in that is 25,000 foot-pounds. That's exactly the amount of work to pull that cable up that was hanging 100 feet. So pretty cool. Excuse me. Must have gotten too excited about calculus. And of course, we like in mathematics to make problems a little bit more interesting. So in your homework, you'll get to do a problem kind of like what I just did. But then at the end of it, I'll say, but what if we put a pail of gravel at the bottom or something? And we can just add all sorts of neat things. We've had lots of problems where there's like a pail of water, but then there's a hole in the bottom. And so it's getting less full of water, which means it's less heavy. So there's all kinds of neat things you can do with this. And that's just kind of an overly complicated way of doing a problem sort of like this. So you can look at that slide if you want to and try to follow it. It is in metric units. So you see the acceleration of gravity in there. But if that bothers you, don't worry about it. No big deal. Just stop the share just for a second. All right, I'm back. I just about coughed up a lung. For whatever reason, I've been coughing a lot lately, but my guess is excessive mask wearing. That's probably what's going on. So good times there. Let's talk about springs. I found this simulator, which is pretty neat. Yeah, the work of stretching a spring. Doesn't it make sense that if you compress or if you stretch a spring, the further you stretch it, the harder it is to stretch it, or the further you compress it, the harder it is to compress it. So there's some resting state of a spring, and you can maybe move it pretty easily at first, but then at some point it's resisting you pretty hard. So we can calculate work for this too, because work is just force times distance. But the force changes. That's why this is a calculus problem. So pretty fun. And what we have to do is there are different stiffnesses in springs. So each spring has what's called a spring constant. And we find this spring constant using what's called Hooke's law, which is that the force on a spring equals negative K, or usually I just write K because you can embed a negative into that if you need it. But times X, X is the distance that you either stretch or compress a spring beyond its resting state. So you can see here, it takes twice as much force to stretch a spring twice as far. It's a linear function that talks about how much harder or how much more force it takes to stretch a different distance. So it's a pretty simple thing. What we want to do most of the time is we're given some information about a particular stretch for a particular spring, and we want to first calculate the spring constant. So we have a number that represents the stiffness of that spring. Now here's Hooke's law in a little simpler form. F equals the spring constant times X, the stretch or compression beyond rest. You can see this particular spring is it's not going to compress anymore. It's kind of at its max compression, but it will be a stretchy spring, as opposed to say maybe a coil under your car, like a spring under a car that is designed so it's compressed so that you have some shock absorption when you're driving down the road. So Hooke's law, I want to take you to this spring simulation because it's kind of neat. It's, oh, well, that didn't work. If I can find my tab with this. Yeah, watch this. So I can just, I can clamp onto this spring and then I can actually pull. So what you can see is if I stretch this spring and I stop, the force right here is 52 newtons. And I've actually stretched this spring 0.258 meters. And this particular spring has a spring constant of 200 Newton meters. But look, I've got a slider here. So I could actually make this spring stiffer if I want to. I can make the spring constant higher. And it's the same force, see, the same force that I've applied, but I'm increasing the spring constant, which means the stiffness is resisting me more. Or I could make the force greater and then it's pulling back. I could make the force less. I could make the stiffness less, right? If I make the stiffness less, but oh, I've got a force that's negative. In this case, I'm actually pushing on the spring. So if I resist it, if I go past this way and I'm pulling on the spring and I have a stiffer versus less stiff spring. So that's kind of fun. You can look at the website and play with this a little bit if you want to kind of understand the relationship between the force, the stretch length, and the spring constant. And again, this is just a number that kind of represents how stiff the spring is or how resistant it is. Stiff spring requires more force. A less stiff spring means the same amount of force can actually pull it further, right? So I thought that was kind of neat that you would like it. So let's do a math problem. This will be fun. As mentioned, work equals the sum of the force function times delta x. But in this case, if we're talking about springs, you just saw it. Hooke's law says the force function is just the spring constant times x, which is the stretch length beyond rest. So again, a spring has a resting length. And let's take a look at this, and I'll pop my whiteboard up in just a second. All right, so we have a force of 8 pounds compressing a 14-inch spring a total of 5 inches. How much work is done in compressing the spring from a length of 12 to a length of 10 inches? I'm just going to write that on my board. So first I'm going to write F equals Kx because that's Hooke's law. And then I'm going to draw a picture with a 14-inch spring. So 14 inches. And then I'm going to represent compressing it 5 inches. So if we compress it 5 inches, it requires 8 pounds of force. Is that everything I need? Oh, and then I want to know, so I'm going to calculate the spring constant first. Then I want to know how much work is done in compressing the spring from 12 inches to 10 inches. So write that in another color. So work required to go from 12 inches to 10 inches. And we can either do this in kind of a more standard unit, like foot-pounds, or we could do it in a less standard unit like inch-pounds, which we'll do it in inch-pounds, but you can always convert that if you wanted to. So here's the information. Force equals the spring constant times X. So the first thing you always want to do in these spring problems is you want to figure out how stiff this spring is and what number should go in here for K. And typically they give you a particular force and stretch combination so that you can solve for K. And this is no different. So 8 pounds of force. So I'm going to put an 8 in the force spot. 8 pounds of force is required to stretch this spring, or actually it's not a stretch, it's a compression. So it works both ways to compress this 5 inches. So 8 equals K times 5. And then if you just divide both sides by 5, you can see that K equals 8/5. So that's just a number that describes the stiffness of this particular spring. And once you know the spring constant, then you can calculate work, because work equals the force function. I should say work equals the integral of the force function, which is K times X, so 8/5 times X, dx. From where to where? Well, I want to go from 12 to 10. Remember, we're compressing this spring. And remember, these values actually represent values of where you're at relative to the resting state of the spring. So the resting state is at 14 inches. And so we're going to already pre-compress to 12 inches, which is 2 inches inside of the 14. And then we're going to compress it to 10, which is, so basically we're compressing this from, say, 12 to 10. So it's just doing this thing from here to here. So we've already pre-stressed it, and we're not calculating the work for it to go from 10 to, or from 14 to 12, but just from 12 to 10, which is 2 inches beyond rest to 4 inches beyond rest. And if you remember, the way that we do this problem, this is called a definite integral. This finds the area under a curve. And this is just a power function. This is x to the 1. So we've got this 8/5. I'm just going to write that 8/5. And then we write x to the 1 more than 1 is x squared divided by that same number. And then I always like to write a line like this. And remember where this is called where I'm evaluating it from. 2 to 4. And all that means is I plug in 4 for x, and then I plug in 2 for x, and I subtract. So let's do that. I'm just going to write the 8/5 out front. So 8/5. Then I'm going to plug in 4 for x. So 4 squared divided by 2 minus 2 squared divided by 2. So that'd be 16 divided by 2, that's 8. And this would be 4 divided by 2, that's 2. So 8 minus 2, this whole thing is 6. So we've actually got 8/5 times 6 over 1. 8 times 6 is 48/5. And if you want that as a decimal, 5 times 9 is 45. 9 3/5, or 9.6. And let's think about these units. We actually did a force in pounds times a distance, and we measured that distance in inches. So this would actually be, we'd say inch pounds, which is kind of funny. Inch pounds is how much work that was required to do that action on that spring. So kind of cool. I love this stuff. And you might think, oh, that's just sort of an out there application. I'll probably never do that in my life. But what you need to realize is this is awesome mathematics. This is math that will blow your mind. This is the stuff that's so cool that we can use it not only in work problems, but all sorts of scenarios where we basically are doing infinity little multiplication problems and adding them up when there are things that are changing that we normally can't handle. So really great stuff. I'm just about done here. I thought that maybe I'd give you, oh, there's that problem if you want to see it on screen with colors. So that's kind of nice. If you want to try one, I'll just give you one to practice. There's a couple problems in the homework too. So a force of 3 pounds is required to stretch a spring 8 inches beyond its resting length of 15 inches. So you could find the spring constant first by plugging in 3 for the force and an 8 inches for the x, the stretch. And then you could calculate the work required by summing up bits of work using a definite integral and going from 18 to 24 inches. So that looks pretty much like the problem we just did. And you can play with that if you want. To close, I just wanted to remind you that the true work of God is to believe in the one he has sent, to believe in the Son, and to find life in his name. I can't do better than that. Thanks for spending time with me. I look forward to seeing you soon.